Hello everyone, my name is Nevena and I'm a fourth-year PhD student in statistics at UT Austin, supervised by Dr. Arya Farahi. And in this video, I'll briefly tell you about our project. The problem that we address here is working with contaminated data. Examples of two such data sets are shown on the slide. In blue, we have target data, which we want to work with, learn from, generate from, etc. And in orange, we have contamination, which for whatever reason cannot be separated from the target data. So we have to be able to work with the full contaminated data set. So let me show you two examples of real-world contaminated data sets. First, we have a data set of MNIST digit images framed in blue, and they're contaminated with images of Japanese characters in orange. Similarly, we have a tabular cement strength data of one age contaminated with cement strength data of a different age group. Now that we have identified the problem, let's set it up. So first, we have a clean data set distributed IID according to P. Then we have a contaminated data set distributed IID according to R, where Q is the target distribution, which we see in blue on the plot, and Z is the contaminating distribution, which we see in orange on the plot. Then we also assume access to a subset L of data points for which we certainly know if they're target or contaminating data. And this is denoted with ij element of L. And finally, we assume access to proxy scores for the entire dataset, so not just subset, which act as probabilities of each point belonging to the target distribution. This is denoted with I tilde j. So our objective is maximum mean discrepancy, or MMD. This is a kernel-based distance measure between two distributions. Now, the problem is when MMD is sort of naively calculated on full contaminated data, it measures the distance between clean and contaminated distributions instead of clean and target distributions, which is what we want to measure. So the solution we propose is what we call CCMMD. CCMMD is an unbiased estimator of MMD. By including audit labels and proxy scores in the calculation, CCMMD actually measures the distance between clean and target data. So let's talk about the results. On the regression example, the results show that CCMMD aligns perfectly with the true regression line, while the competitors struggle. On the right-hand side, we can see that performance also doesn't deteriorate with increasing contamination rate. In a more demanding task, when CCMMD is used in image generation, we again see that CCMMD outperforms competitors across the architectures. There is no performance degradation with increasing contamination rate. And also the FID plot shows that the quality of the generated images doesn't deteriorate with increasing contamination rate. At the end, we can conclude that with CCMMD, contaminated data doesn't have to mean unusable data. CCMMD combines audit labels and proxy scores, and it is robust by design on contaminated data. Also, it works with various data types and applications. We're excited to explore open questions in the future. Thank you very much.